Good morning, students. So last time we have done the Poisson process and compound Poisson process. So today we are going to start with the continuous time Markov chain. Let me share. Okay, so I think my screen is now visible. Okay, so we are starting with the continuous time Markov chain. Okay, CTMC. So definition is let xt be the state at time t. Xt is continuous time Markov chain if for all s and t greater than 0, and kindly mute yourself. When some question is there, then you unmute. Okay. Xt is continuous time Markov chain if for all s and t greater than 0 and for non-negative integers ij, xu, u is greater than 0 less than s, probability xt plus s is equal to j given xs is equal to I, xu is equal to xu, u is greater than 0 less than s. So this basically conditional probability. So this is same thing that the future will depend, given the present and past will depend on the present only. So that is probability xt plus s is equal to j given xs is equal to I. So here note down that xt is state at time t and xt is a continuous time Markov chain, and xt is basically taking discrete value. So therefore this is discrete state and continuous time stochastic process, continuous parameter stochastic process. So I, j and xu are the basically state space values. So xt plus s is equal to j given xs is equal to I, xu is equal to xu, u is between 0 to s is probability xt plus s is equal to j given xu is equal to I. Now we are saying that this is equal to p I j t. This is equal to the transition probability Pijt. That means this is we are also making this independent of s also. If probability x t plus s is equal to j given x is equal to I is independent of s, then continuous time Markov chain is said to have stationary or homogeneous transition probabilities. Okay, so this is basically PIJT. This depends on the I initial state, final state, and the time t also, independent of s we are taking, then this is called stationary or homogeneous transition probability. So there are many applications of continuous time Markov chain. So in the queuing system where some customers are coming according to some process, then they are processed in the server and then they leave the system. So there are some, for example, there are some programs are coming to be processed in the server, then they are processed and then they are leaving the system. So then these kind of systems are there. So let me give another definition first of all. Let me just take first equivalent definition of this. So,
Sir,
yes.
sir, please scroll a bit. Sir, in this, the third line, I don't understand. After what is written after non-negative integers ij?
Ij and xu, x bracket. So this is also some integer basically I am taking, so that basically u is basically like this, taking this value.
So state is an integer, right?
State, yeah. So because this is continuous time Markov chain. So xt basically taking values. So just to denote that thing basically. So otherwise you can write x ui is equal to some ui also.
Okay, sir, got it.
So time is basically continuous here. U is continuous. Whether I'm audible?
Yes, sir.
Okay, so basically it is saying that time is continuous basically. So basically you are saying, for example, uh, basically some customers are coming. Okay, so to the bank, then xt is number of customers in the interval 0 to t. Okay, so xt is taking basically discrete values. This is basically discrete. Oh, some examples I have given. Let me just show you that examples. Uh, your when I have started this. So basically, I am taking about the talking about the your continuous time discrete states. Okay, for example, this example I have taken. Discrete state continuous parameter stochastic process. Xt is number of jobs in the system at time t. So some queuing system with jobs arriving at random in time and queuing in service and departing from the service after service completion. So xt is number of jobs. So xt is taking values 0, 1, 2, 3 and so on. T is basically t such that t is greater than 0. So therefore this is this type of values are there. Okay. So this is basically t is basically your continuous. So this like that it is you can take.
Sir, one more thing.
Yes.
Sir, in the definition, that p of x of t plus s equals j, given that x of s is equal to I. I do not understand what is this part written. X of u equals small x of u.
Yeah, so uh, because this is u is continuous basically, u is continuous value taking. So values taken by xu is basically discrete values. So that is the thing. Basically, u is varying continuously. Okay, time is continuously varying. So that is the thing basically. That it does not depend on the, for example, xt plus s is some value j. Okay, in some state it is in some state j at some time. Okay, and we know that for u greater than equal to 0 less than equal to s, the process is taking value xu. For example, some some function of xu it is taking. So that also maybe you take some value of u, some value it will take. So that is the thing basically. Yeah. Okay, so let me take let ti denote the sojourn time or the amount of time the process stays in state I before making a transition into a different state. Okay, so Ti is the sojourn time or the amount of time the process stays in state I before making a transition to different state. Then using star, basically I can take this as star. Okay, we have. So now, okay, so it is saying that Ti is the amount of time the process stays in state I before making a transition into different state. So probability Ti greater than s plus t given Ti greater than s is probability Ti greater than t for all s and t greater than 0. So it is saying that the amount of time process stays in state I before making a transition to different state. Then using star, because it we are saying that it is independent of s. So x this transition probability is same as that of probability xt is equal to j given x naught is equal to I. So therefore it is Markovian. Basically it doesn't depend on s here. Okay, so therefore Ti the greater than s plus t amount of time the process stays in state I before making transition to different state is basically Ti greater than t basically. So this implies that Ti is exponential with the parameter, let us say Vi. So we are saying with parameter Vi, so that Vi we have to determine basically. So from here, because of this, the stochastic process having the property that each time the process enter state I, the amount of time it spends in that state before making a transition into different state is exponentially distributed. with mean 1 by Vi. So same thing we are saying, what we are saying in the sojourn time. And second thing we are saying is when the process leaves state I, it next enters state J with some probability, say Pij. Okay, so some probability Pij enters. So this Pij is different from this Pijt. Pijt was transition probability, and Pij is the probability that each time when the process enters state J, the process when process leaves the state J, it next enters state J with some probability. That is Pij. So Pij must satisfy Pii is equal to 0 for all I, and summation J Pij is equal to 1, because it should be somewhere in total probability should be 1 basically. Okay, so any question till now?
Sir, how did you reach the conclusion that it is an exponential? It is
Yeah,
rise.
because of this property, because we have done this thing that probability xt greater than s plus t given x ti is equal to greater than s is probability ti greater than t. When this happens, that means that ti will satisfy this thing, and this also implies that ti is basically exponential because of this basically. Because if this relation is satisfied, then we conclude that thing.
Okay, sir.
Sir, what
So
was
do you
VI
need the
here?
proof? Vi is some parameter basically denoting of for state I, because it is exponential we know, so some parameter will be there for exponential distribution. That is the thing. So for example, I am just saying this. For example, mm, you can just easily check that ti is when exponential, then this will satisfy this thing basically. This is the, what is the reliability function of exponential distribution? Anybody? What is the CDF of the exponential distribution?
E to the power minus lambda t.
That is the, yeah, e raised to the power minus lambda is the reliability function. CDF is 1 minus of that. So you can clearly see that this value is uh, probability that ti greater than s plus t, ti greater than s divided by probability ti greater than s. So this value is the probability ti greater than s plus t divided by probability ti greater than s. So this value is e raised to power minus, if I take ti is equal to this value, e raised to power minus uh, vi s plus t divided by e raised to power minus vis. So therefore this is e raised to power minus vi t, which is nothing but probability ti greater than t, because if I put this value also, this answer I will get, e raised to power minus vit. So if I take the exponential distribution, then clearly this will satisfy this thing first of all. Now second part would be basically to showing that if this is satisfied, then ti will be exponential. So for that, yeah, so Yeah. So do you need the proof of other part also? It is clear that exponential distribution will satisfy this property.
Yes, sir.
Okay, so next time I will provide you the proof of that because that proof is will be lengthy one. So let me just next time I will show you that thing. So okay, so that next time I will show you that proof. Okay, so one thing you can easily see that if this Markovian property is satisfied, that Ti is exponential, this will satisfy this property. Then other part next time I will show you that proof I will give you if you need that. Okay. So okay, any other question?
Sir, is there no concept of transitioning into itself? I mean, the state won't change.
That probability is zero, na? Probability is zero. Pi. Basically, when process leave state I, next enter state J. So transition to. So that will be, I think, uh, Pi. You are asking PIIT basically.
Yes, sir.
Yeah, I think that is possible. Yeah. So that is because after time t is there. So that is also because j we have not specified here that j is maybe may not take I value also. That is not we have not given.
Yes, sir. That's what I'm saying. We have already assumed that it won't go into I. So what if it does not do that? And
No, that is basically that amount of time it spends in state before beginning transition. Different state is exponentially distributed with the mean because that will be exponentially distributed basically. So that is the thing basically. Yeah. It will stay in that state before making the transition is basically exponential. Will follow exponential distribution with mean 1 by Vi. That is the thing we are talking here. Because it is independent of, because xt plus s is equal to j given xs is equal to I is probability xt is equal to j given x naught is equal to I. Okay. Okay, so
Sir,
is it
yes, we have a concept of steps. Like we don't see in one step or two step. We will see only like in time t. Is it not so?
because it is continuous time, na? Continuous time it is. Discrete time we have already done. Discrete time Markov chain we have done, na, where we are basically times are like this. So here time is continuous. Is it okay?
Yes, sir. It is fine.
Yeah. So discrete time we have already done. Discrete time Markov chain we have done. This is continuous time Markov chain. So yeah. Now let us take some examples of this. So let us give some examples. Birth and death process. Okay, so consider a system whose state at any time is represented by the number of people in the system at that time. Okay, so suppose whenever there are n people in the system, so whenever there are n people in the system, xt is the number of people in the system at time t. Okay, then new arrival in the is exponential with new arrival enter the system at exponential rate. So that means xt plus h is equal to n plus 1 given xt is equal to n is lambda nh plus small h. That is in a very small interval because exponential distribution has, so whenever there are n people in the system, there are n people in the system, then new arrival enter the system at an exponential rate lambda n. So we know that exponential distribution and Poisson process are related. So isn't it? So therefore, whenever there are n people in the system, new arrival in a very small interval h is small. So therefore, that will follow lambda h plus small oh. It is clear. Okay. Also, okay, yeah. Also, we are assuming that people, whenever there are n people in the system, people leave the system at an exponential rate mu n. So that means probability x t plus h is equal to n minus 1. That means one people is leaving. V is basically, let us say, is equal to mu nh plus small h. There will be some parameter mu nh corresponding to that. H is small. So here lambda n is called the arrival or birth rate, and mu n is from 1 to infinity, is called departure or death rate. Okay, so basically there are in the system, that is say zero members, 1 members, n minus 1 members, n members, n plus 1 members, and so on. So when 0 members there, then arrival rate is lambda naught. Okay, and when there is 1 member, departure rate is mu1. When there are n minus 1 member, arrival rate is lambda n minus 1. And when there are n members in the system, departure rate is mu n members, arrival rate is mu n. And when there are n plus 1 members, departure rate is mu n plus 1. So this is known as the state transition diagram. Okay, so this is the state transition diagram. Okay, so in the birth and death process, so this is known as the birth and death process. Okay, so in the birth and death process is a continuous time Markov chain with the states 0, 1, 2, 3, and so on, from in which the process can go from n to n plus 1 or n minus 1. Okay, so at what rate we can go from state 0. Okay. So let us say, first of all, for state I, let us say state I we want to see, or state, let us say n we can say, because n we are taking. So state n. So Vn, what is Vn? Vn is basically corresponding to Ti. Ti is the sojourn time or the amount of time process state in state I before making a transition to different state. So we know that x is exponential with the rate lambda n. That means the one customer can enter with the rate exponential rate. New arrival is according to exponential with the rate lambda n when there are n person in the system, and they can leave. One person can leave with an exponential rate with the exponential distribution with the rate mu n. Okay, and assuming that both of them are independent, then what is the sojourn time is exponential with the rate some Vn. So then what is Vn basically? So this is nothing but amount of time the process basically, since the time until the birth and death occur is exponential. So since time until either a birth or death occur is exponentially distributed with rate lambda n plus mu n. Why? Because when you leave the system, whenever there is either arrival or departure, so whichever occurs first, that means minimum of x comma y. What is the distribution of minimum of x comma y? Can anyone tell? If x is exponential, y is exponential, both of them are independent, what is the distribution of minimum of x comma y? Yes, anyone? So can anyone just give it a hint how to calculate? X is exponential, y is exponential, minimum of x comma y. Minimum is greater than x, let us say some z, both of them, that means x is greater than z, y is greater than z, both of them are independent, that means x is greater than z, probability y is greater than z. What is the reliability function of x? E raised to power minus lambda n z. What is the reliability function? Mu n z, e raised to power minus lambda n plus mu n plus, which is this distribution? Reliability function of which distribution?
Exponential.
Yeah, clearly minimum is exponential with parameter lambda n plus mu n. Okay, so basically the time until either a birth or death occur is exponential with the rate lambda n plus mu n. So therefore parameter Vn. Okay, if the stochastic process having the property that each time process enters state n, amount of time is spent in state n before making a transition to different state is exponential with the mean 1 by Vi. So Vi here is lambda n plus mu n. Similarly, for V naught, because no departure is there, so therefore that that will be lambda naught, basically clearly lambda naught only. Okay, so now what is P n2n plus 1? P n2n plus 1. When the process leaves state n, state I, it next enters state j with some probability Pij. So let us determine this probability, because in the birth and death process, from n to n plus 1 we can go, or n minus 1 we can go. Okay, so therefore P n to n plus 1. So this can occur when there is a birth before a death. Then only we can go from n to n plus 1. Otherwise, if death occur first, then we go from n to n minus 1. Okay, so therefore, but birth is exponential with parameter lambda n. So x occur before death. So now this is using theorem of total probability, that this can be written as 0 to infinity probability that y is greater than small x, because x and y are independent, given x is equal to small x. Okay, or you can write down like this also. Okay, f into the density of x, that will be lambda n e raised to power minus lambda n x dx. Okay, so but x and y are independent, so therefore this first of all this x becomes small x, and also we know that x and your y and x are independent, so therefore this becomes like this. Okay, so therefore this is 0 to infinity, but also we know that y is exponential, so therefore this is e raised to power minus mu n x, and this is lambda n e raised to power minus lambda n x dx. So therefore this is lambda n 0 to infinity e raised to power minus lambda n plus mu n x dx, which is equal to lambda n upon lambda n plus mu n. Okay, so this is the probability that you can go p n to n and n to n plus 1 basically. So when the process is in state n, it next enters state n plus 1 in the birth and death process. Now, what is this value equal to? P n to n minus 1?
Sir, mu n upon lambda n plus mu n.
Yes, yeah, clearly, because you just replace the roles of them. So clearly this will be mu n upon lambda n plus mu n. It is clear that this will be this value equal to this. And P01, because we know that from 0 to 1 only we can go. Okay, so that means this probability will be one clearly. Okay, so this is therefore equal to 1 only. All right. So this is about the birth and death process. So anyone had any question in birth and death process? By definition 2, it is a continuous time Markov chain also.
Sir, is this a continuous form of the gambler's rune?
Gambler's ruin.
Except the part where
Why
it
you are
went to n.
asking that gamblers? Why gamblers ruin is coming here? No, gamblers ruin is different. In gamblers ruin you have n, basically I, rupees I, gambler has rupees I, his aim is to achieve rupees n. So that is the different problem basically.
No, sir, I'm talking about the diagram. Diagram is similar to that.
But
Except that
here
there is no
states
limit.
this is continuous time Markov chain. No? That is the thing. It is a continuous. That is a discrete time Markov chain. That is a discrete time Markov chain. State transition diagram we are representing here. So, okay, so I think next is that is just a representation in terms of diagram. We can say that is the thing. Okay, so but that is discrete. Here is it is continuous basically. Okay, so let us take second example, Poisson process. Although we have studied the Poisson process in detail also, but clearly Poisson process is a birth and death process where your lambda n is equal to lambda and mu n is equal to 0. Okay, so this is the basically Poisson process. So a process in which departure never occur and the time between successive arrival with mean 1 by lambda. So hence just a Poisson. So we have seen that your Poisson process is also a birth and death process. That means this is also a continuous time Markov chain also. Okay, so pure birth process. So pure birth process is also a birth and death process. So in which we have the birth rate lambda n and death rate is 0 for all n. So whether this is a Poisson process is also a pure birth process. This question is whether Poisson process is also a pure birth process.
Yes, sir.
Yeah, so in this case lambda n is equal to lambda basically. Okay, so next is the Yule process or a birth process with linear birth rate okay, with the linear birth rate, okay, Yule process or a birth process with linear birth rate. So it is a pure birth process with lambda n is equal to n lambda. So what is the meaning of this? That means each individual in the population is assumed to give birth at an exponential rate lambda. Okay. So if each individual can give is assumed to give birth at an exponential rate lambda, so if there are n per person in the system, then lambda n becomes basically n lambda, minimum of Okay, so can anyone explain this? How this is n lambda? If there are here each individual in the population is assumed to give birth at an exponential rate lambda. So can anyone explain how lambda n is n lambda? So there are basically n persons, and let us say xn is equal to n in the population at time t. So then each individual is assumed to give birth exponential rate lambda. So x1, x2, let us say x1, x2, xn are there. So lambda n. So lambda n will be basically one birth can take place. So that means minimum of x1 so on to xn. Whenever there is a one birth, that means minimum of x1 so on to xn. So that will be xi's are exponential. So minimum of them will be exponential n lambda. Is it okay? Is it clear or not? Yes or no?
Yes, sir.
Yeah. So therefore, n person are there. So x1, x2, xn, each of them is exponential lambda. So whenever birth is taking place, so whenever minimum of them will give a birth. So therefore minimum of x1 so on to xn. So that means that is this exponential distributed with parameter n lambda. Okay. Okay. Now this is fifth example is a linear growth model with immigration. So in this model, lambda n is equal to n lambda plus theta and mu n is equal to n mu n is greater than equal to 1. So can anybody explain this model? Seeing this is a birth and death process with lambda n is equal to n lambda plus theta and mu n is equal to n mu. So can anybody explain? If there are n person in the xn is equal to n at time t, n persons are there. So birth can take place. Each member can give birth. So with the rate lambda, So therefore n lambda and some exponential rate of increase theta due to external source such as immigration. So this theta is due to some immigration factor and each member can die also. So therefore y1, y2, yn, those are exponential with parameter mu. So minimum of them will be n mu. So therefore this is the case. So here each individual population is assumed to give birth at exponential rate lambda. In addition, there is an exponential rate of increased theta of the population due to external source such as immigration. Okay, so therefore lambda n is n lambda plus theta, mu n is equal to n mu. Okay, so what is whether this previous fifth model is clear, linear growth model with immigration, or any question is remaining, how these parameters and how application of this is there. Yes, you have to say either yes or no, whether explained, whether it's clear or not.
Sir, how do we explain theta in this model?
Yeah, so first of all, there are, let us say, n person in the population. Each person can give birth at exponential rate lambda. So therefore, n lambda will become, because lambda n, because of x1, x2, xn, minimum of that. Okay, x1 so on to xn. So now, because birth will then take place, minimum of them. Okay, then this theta is due to some external source. Some addition of in the population is there due to some external source such as immigration. So this is some external source, because the population can come from outside also in the population, not from the birth also. So taking care of that, we are writing this. Is it okay? To take care
Yes,
of that
sir.
thing. So let us stop here. So any question till now which is not clear? Today's class. Okay, so let us stop here.
Hello, sir.
Yes.
Sir, we have defined lambda n as n lambda. So can we not think in this way that if there are n people at present, then probability from n to n plus 1 can be they can be independent for each n. So it will be product of all exponential distributions. So it will be lambda n.
No, why product? Because each of them, if each of them give birth, then because this is a birth and death process, because we cannot directly move from n to n plus n, we have to go from n to n plus 1 first. Okay, then so there is a birth, so that means birth, because this is a birth and death process, so we have to basically minimum of each can give birth. So how we will move from n to n plus 1 state, n state to n plus 1 state? Whenever any one of them give birth, whichever give birth first, that will take us to this n to n plus 1. Okay, in that fashion you have to think.
Okay, sir.
Because xt is equal to n, then in the next state will be n plus 1. Okay, so that like that. Okay, so how that is coming basically, that we are explaining basically here. Okay, let us stop here.